Hi everyone, I'm Nori, and today I'm presenting what kind of useful information we can extract from this IRIS Wavefield experiment. And here at the beginning, I'd like to acknowledge the people at the IRIS DMC, and the Pascal to organize the data set and for observations, the node owners, many universities, and the people who deployed sensors, because the summer in Oklahoma is really hot. Okay, so this is the shape of the array. This is central, north central Oklahoma. And the array size is about like 13 by 5 square kilometers. And there are 365 three-component geophones, 5 Hz geophones, and 18 broadband sensors. As you can see, that the shape of the array is really unique, like two vertical and one horizontal lines, and also small 2D arrays and several triangle shapes. And this is the observed data we obtained. So this is 1 hour observed data in the up-down vertical component. Because of the shape of the array, the data vertical axis is something not very easy to understand. But from the bottom to 129 traces are related to the this east-west line and vertical lines and so on and so forth. And the horizontal component is time. Then we can see that there are many interesting signals that run like vertical black lines are all related to earthquake events, and also there are some other noises we can see. To check the data qualities, first look at the observed data in the power spectrum. There's one very interesting location of the sensors, like inside of this blue circle. There are like 3 different types of sensors deployed, like broadband sensor, buried geophones, and surface geophones are deployed at the same locations. So we can check the data quality by using these sensors. And the noise level of the broadband sensor is actually quite nice, and like higher than 10 second period, we can see some like very clear nice signals, and the noise level is not very high either. Maybe if we want to use a long period horizontal component, we need to be careful, but other than that, the quality of data, I would say, is very good. Compared with that, buried geophones shows a little bit higher noise levels, like higher than the like 0.5 Hertz, like around here. We can see that the shape of the power PSD is the same, but all noise levels are actually elevated. That is related to the quality between geophone and broadband sensors. And the very long period part is probably very hard to use, because that is more related to the noise level of the sensor itself. Compared with that, surface geophones are actually much more noisier. Like vertical component is something comparable. It's a little bit higher, but it's still comparable. But like horizontal component is really noisy. So we need to be careful, like if you want to use this kind of sensors. Note that all geophone sensors except this surface sensor is all valid. So we can use the geophone as this quality. So that would be great, and we can do a lot of processing with this data set. Okay, to see the continuous observation, beamforming is a very powerful tool, and this is a vertical component beamforming result. And beamforming is done by using this east side 2D array. And this is 3 different frequencies, like lower frequency, intermediate, and high frequencies. This is averaged over 2 weeks, and these bright spots showing the wave velocity and also the directionality of the continuous data. So most likely the noise comes from the south side of the array, and with different frequencies. Mainly what you can see here is mainly like the surface waves, like low frequency surface wave is stronger and high frequency is getting, low frequency surface wave is like faster and high frequency is slower. Of course, the beams are not stable over the 2 weeks, and this is the hourly beam forms, and it actually varies a lot. And but like mainly like the velocity speed is 1.5 kilometer per second here, and this is more likely 350 meter per second. Okay. So back to the observed data, and we have a lot of signals we can find, and let's start with ambient noise correlation studies, and then I will talk later about the earthquake studies as well. So this is the ambient noise correlation. So we have the background noise, and we can use this for extracting some useful signals. So this is a 0.5 to 3 hertz. And I cross-correlate the data at the yellow star with all other components, and this is each trace is showing the cross-correlation between each receiver pair. And this white dot showing the arrival time of the 1 kilometer per second waves. So I would say that the signals are very coherent over the traces, like the waves are very coherent over traces, and we can clearly see the arrivals. One of the problem is because you can see from this shape, you see that this shape is not very ideal for the imaging or tomography, and we need to confirm that the reliability of the cross correlation functions, like that is well represented to the Green's function or not. So even high frequencies, we have the signals are much more symmetric, but not perfectly, and we have some weird signals that might be related to the directionality of the noise sources. So can we actually somehow do the signal processing to enhance the reliability of this cross correlation? That is the question I'd like to address in this talk. So noise correlation, average noise correlation is the sum over the hourly or daily cross correlations. So this is like each hour I compute the cross correlations, and this is average correlations I showed. Noise directionality is the same game. So this is the average noise correlations, and they are like a sum over the many different hour directionalities. So because the noise distribution is not homogeneous, according to the azimuths, there are some distortion in the cross correlation functions. For example, like noise comes from the south side, and there are some signals, some like strong energy around the zero lag, or like from the east side, and most data are in the equator time, or something like that. So can we numerically reduce the directionality? Like we usually assume that if we have enough data and average over the like 30 days or 1 year, we can reduce this directionality. But in this data set, that is not the case. So can we numerically reduce this directionality? I propose a very like simple way to overcome these limitations. So I put the weighting parameters at each hour and do the summation with this weight, and try to make these beams more homogeneous. I also use the penalty functions because that stabilize inversion. Then objective of this inversion is find the weight to homogenize the noise directions, and the goal is to use the same weight estimated from the beamforming for the better quality correlation functions. Of course, we need to define what the better quality correlation functions means, but I will discuss it in a minute. So let's jump into the results. So this is before weighting. So this is simply I average over the entire time. This is after weighting. So this is before, after. So it looks like something very small changes, like this is more likely southeast, and this part is a little bit more circle. And if we draw one contour line, it looks like more circle. So that's a small changes, but this is very important changes for the noise correlation functions. And also, like I should say that the array size of the 2D array is not really big enough to solve the multiple waves in these frequency ranges, but there are some still like we can do some weighting. So let's look at the correlation functions. This is before vertical component. This is just simple sum, and this is after. After weighting, before, after, before, and after. So we find that, for example, we have some noise suppression inside of this red circle, after, before, after. So we basically reduce the unwanted noises, and also we enhance some signals inside of this blue circles, after, before, after. And these signals are actually much more coherent than without having the weighting function. So that enhances the reliabilities. So with this weight sum procedures, we can actually get the correlation functions a little bit more reliable and useful for the imaging purpose. There is some assumptions, of course, and the assumption I have, the weak assumption is the noise at the 2D array. The 2D small array on the east side represents the noise condition at the entire array. That's one of the assumptions. And there are some pros, and we don't need to have the assumption for the shape of the cross correlation functions. For example, like I didn't assume the cross correlation function has to be symmetric, but after this weight sum, the correlation function is actually more symmetric than before. And we don't need a full 2D arrays. Like for extraction of the reliable grid functions, having the full 2D arrays is very good, but sometimes it's difficult because of the economical reason or environmental reasons. And this procedure needs some small 2D arrays to correct the grid function more useful. Okay, I realized that after doing this weighting sum, the TT component becomes very symmetric and very easy to use for the tomographic study. So I use this TT component for the tomography. So this is from that TT component, I invert the lab wave group velocities. This is one frequency slice. And we can find some like small features like fast velocities in blue and slow velocities in red. So this shape, these features are actually much smaller than the geologic map we have, but there are several interesting features we find. Right now, what I'm doing is I'm using a much lower frequencies to see the velocity changes in the basement. Okay, so this is the information I extracted so far from the background noise, and let's move on to the small earthquake detection part. So this is also the very interesting part using this data set that. Of course, because Oklahoma is famous for induced seismicity, and there are a lot of earthquakes we find. And one event on catalog in this hour that is here, which is magnitude 2.2, and looks like very black lines, black vertical lines. But if we magnify this data, we can actually very clearly see the hyperbola. So this is the hyperbola of P waves, and also we can see very clear hyperbola of S waves. And some coda waves are also clearly observed. So that would be great, and we can actually use this for many different things, like locating or also the mechanism estimations. So the reason why we have very good hyperbola is because, of course, like we have very dense array, that is very useful. Also, these clear signals are useful for estimating the moment tensor or focal mechanisms. So if we find the the polarity of the first arrival or amplitude of the first arrival and plot it on the map, we can see the radiation pattern of the first arrivals that is directly related to the focal mechanism. So we can use this for the focal mechanism estimation as well, and the uncertainty of this focal mechanism is actually much smaller than using only sparse arrays. Okay, then on the catalog we find only this magnitude 2.2 array, but because we have local arrays, we have much more signals. Like we can see like very many like black vertical lines, and this is other earthquakes. And for this detection, I use the template matching technique plus hyperbola assumptions. Like I assume the waveforms are hyperbola and calculating the hyperbola to detect them and also locate them. Then I use the entire 3-component data set. So these waveforms are actually very interesting. That within 10 seconds we have actually 3 earthquakes, 3 small earthquakes, magnitude 2 about, and the location is almost the same, and the waveforms are also very similar each other. We can see much smaller events. You can probably barely still see the waveforms here, but when we magnify it, we can still have the, very clear hyperbolas, and we can estimate the location from there. This is probably almost not visible from the entire observed data, and without detection technique, it's very hard to find. This is magnitude -1, and we can still see the hyperbola if we know the location, if we know the travel time, and we can use this hyperbola to locate them. So from this 1 hour of data, we can find 32 events, and that is located based on this hyperbola and 1D velocity model, and this is the location we find. So most likely the events are concentrated around here, and this is we know that this is some nest of the earthquakes from the ODS catalogs, and there are some events we find as well. I didn't locate them, but if we scan entire data set with a template, we detect that 20,000 events from the entire 1 month. And this 20,000 is all of them we have the hyperbola, which means this 20,000 events are all inside of these map areas. And I'm right now locating them. So to conclude my talk, I use this IRIS data set, and that is very interesting data set, and we can use this data set and for the earthquake detection and location, and we find very interesting earthquake sequences, and also like we can use the amplitude for the mechanism estimation, and hopefully we can also use understanding the physics of the induced seismicities. And also we can use the background noise for the ambient noise correlations, and we need to be careful because the shape is not very ideal for imaging or tomography, but we can use these ambient noise correlations for the imaging of the structures and finding the very small features. Thank you very much, and I'd like to happy to get some questions.
Great. Thanks very much, Nori. That was fabulous. We have had a few questions come in so far, but any of you out there listening, if you have questions for Nori, now is the time to go ahead and type those into the chat box and send those in to me so that I can pose those to Nori. One question that came in, Nori, let me just grab it here. There was a question about how did you evaluate the weighting functions used to enhance the signal directionality?
So I didn't really evaluate the weighting functions. That is simply like I mean to find the weighting functions. So where is it? Okay, good. So like I calculate the average energy at each azimuth, and so I have the function of the energy against the azimuth, and with this weighting function, I try to minimize the variation over this azimuth, and that eventually makes the similar or almost same energies come from the entire all different azimuths.
Okay, great. We had a question come in about your earthquake locations. Do you have any information on the depth range of those earthquake locations?
That's great questions. So far, I still don't have much confidence about the depth, but so far, it looks like around 4 to 5 kilometer per second, 4 to 5 kilometer depth. Some of them show much smaller uncertainty, but I'm double checking right now.
All right, great. It's a question that just came in. Have you performed receiver function study using the data set?
Yes, I did. I used local earthquakes, that is like within 100 to 500 kilometer away from the array, and try to estimate the depth of the basement. I didn't have any additional slide, but I'm doing it.
All right. Well, I think that looks like that might be all the questions that have come in so far. If Chuck is ready, maybe we'll go ahead and switch over to him. And if you have additional questions for Nori, feel free to keep sending those in. And if there's additional time at the end, we can take care of them then, or I can pass them along to him. Thank you very much, Nori, for that fabulous presentation. It was extremely interesting. Chuck, if you're ready to go, I'll go ahead and switch over to your screen here.
Okay, I'm all set.
Okay, while you're getting set up, let me just give you a brief introduction here. So our second speaker today is Dr. Charles Langston, who is currently the director of the Center for Earthquake Research and Information at the University of Memphis. Chuck received his PhD in 1976 from Caltech, and his research interests include a wide range of geophysical studies, including a new wave analysis technique known as wave gradiometry, about which he will have more to say in today's talk. Today he's going to be discussing his initial results from the IRIS Wavefields dataset, and without further ado, here is Chuck to present arrays and gradiometers of the IRIS Wavefields community experiment.
Thank you, Justin. Well, good day to everyone out on the web, and thank you for listening in. I promised to say hi to the IRIS Pascal people who are watching, particularly Akram Mostafanajad, who left the steamy heat of Memphis for the dry heat of Socorro. Hi, Akram. Today I want to talk about some of my research on phased arrays, gradiometers, and the IRIS Wavefield experiments. But first, you have to acknowledge the the people who made all this possible, the National Science Foundation. I'll be talking about some data that I got from Frank Vernon at UCSD a little bit later. And of course, the IRIS organization, the DMC for providing data, and certainly the Wavefields experiment people, Ken Anderson, Justin Sweet, Bob Woodward, and all the hosts of graduate students, Pascal field engineers, and co-investigators who were out there for the experiment. So my motivation is basically to, I'm really interested in arrays to understand the composition of seismograms to infer both source and structure information. Phased arrays and gradiometers can give important information on wave speeds, azimuths, and wave amplitude behavior that can be used to understand wave propagation in the Earth and atmosphere. Recent large N efforts like the Oklahoma experiment are also allowing some relatively new concepts to be tested with field data. Personally, I've been waiting for the Wavefields experiment for 10 years, and that I can now rigorously test some ideas on the theory and application of wave gradiometry for analyzing seismic waves. Let's review the experiment geometry a little bit more from a slightly different viewpoint. There are all sorts of arrays, two-dimensional phased arrays within this experiment. There is my little baby here, the 7-level recursive gradiometer in the solid blue dots. The GOLE 3x6 array, the broadband array, was set out and associated with some of those elements are the infrasound arrays from SMU. And during the experiment, we also had some nodal seismometers left over. So we densified the places where the two lines cross each other. And I like to call these kind of a variable aperture cross array, which you could make the aperture as big as the experiment if you'd like, or as small as some of the smaller station. And of course, we just heard about the whole thing, which is one really odd-shaped regional array with high frequency and broadband elements. So let me talk about the what I consider the sort of the broadband phase array part. This is the GOLA 3x6 array geometry. On your left here is the ideal geometry that was designed by Fred Folwell a number of years ago, which is kind of unusual. If we look at the geometry, it looks like it's a very sparse array made of these tripartite subarrays. But if you look at the co-array diagram, which is simply plotting all of the distances and azimuths of every pair of station on another spatial diagram, you can see that this seems to say that we can sample a wavelength across this spatial area fairly uniformly with this odd arrangement of sparse seismometers. Now in the field, there are constraints. The tripartite arrays were put in very nicely in quarter sections of farm fields, and so they could fit in very nicely. But finding the appropriate quarter sections to agree with this geometry was kind of tough. Some people didn't allow instruments on their land, so they had to be moved. And so the array geometry is sort of the first problem. If we look at the co-array for the actual array geometry, you can see that it's not sampling the wave field uniformly, and that there's kind of holes in the possible response. Well, if we look at the broadband frequency wave number spectrum, these are plots of in 3 frequency bands: low frequency of 0.3 to 1 hertz, 1 to 2 hertz, and 5 to 8 hertz. You can see the response to a vertical traveling plane wave with this frequency content. The ideal array geometry has a very symmetric response, and it really focuses down to a point at this scale. This is east-west slowness from 0 to 0.5 second per kilometer, and this is north-south slowness. The ideal geometry is pretty nice, but the field geometry isn't too bad either. We pick up some side lobes from the non-ideal geometry, but it still focuses, in a theoretical sense, these plane waves. So one of my questions, and I just answered this thing this morning, actually, is it really possible? Can we make this array focus down on high frequencies like this? Usually with a phased array, when you go to high frequency, the scattering under the array, the Earth is a very important part of the array itself, that if there's a substantial scattering of the waves, then the waves will not correlate and you can't stack them up as a function of slowness and azimuth, and basically you get a mess. So an experiment is to see, is this really possible? Can this array perform as advertised? So I took data from, this is P-wave data, from the magnitude 4.2 Fairview, Oklahoma earthquake that occurred in July last year. And here is the 1 to 2 hertz broadband slowness plot. The actual back estimate of the earthquake is 262.5 degrees. And with 1 to 2 hertz band, we see it's pretty close, 258 degrees. But when we go to high frequency, 5 to 8 hertz, this is astounding to me. The array response has a little bit of aliasing. You can see these little whales all over the place, but there's a really sharp high peak at where we expect it, which is just spot on to the back azimuth. And it gives this is the P wave, and we have a slowness of 0.16. That's about 6 kilometers per second for this earthquake, which is it's roughly 100 kilometers away. So I am totally amazed that this array can perform so well. because the high frequencies have to correlate to be able to, over the entire array, to be able to focus a wave like this. So that's one of my first results with the array experiment and phased arrays. Now, a gradiometer is a phased array. Nori was using it as a phased array to stack noise traces. But the experiment itself was set out that the square part of the square arrays were set out to test how well a gradiometer can perform relative to a phased array. And so here is one square of the 7 squares of the gradiometer, and it has to be, the square dimension has to be much less than a wavelength, 1/10 of a wavelength or less to even 1% of a wavelength, to be able to calculate an appropriate spatial derivative of the wave field across the gradiometer and to evaluate it within this subarray. And when you do that, you can then take the spatial derivatives and the wave field itself and figure out wave azimuth, wave slowness, and whatnot, and all the same things that you can do with a phased array. Here is an example of the data. Nori did a gangbusters job on showing all the data. I like to really look down at the details. I like to look at the waveforms. I really want to know what the composition of the seismograms, what phases are in the seismograms, and how you can use them to figure out source and structure parameters. And so here's a magnitude 2.9 event, which is roughly 50 kilometers away. This was June 23rd, so not all the sensors of the GOLE were in, but there 12 of them were, and it shows an amazingly correlated set of waveforms across there with body waves and then surface wave trains coming in across the array. The gradiometer data for that earthquake is also very impressive. We see body wave arrivals and surface wave arrivals. If we stack all of the vertical components for the gradiometer, we see that they stack pretty well. That there's very little variation in amplitude and phase across that gradiometer, which is sort of portending well for being able to calculate good spatial gradients. So here's the problem that I've investigated so far and talked about it at the SSA meeting. When you put in, when a theoretician or someone who uses the data wants to analyze the data, they want perfect data. They want the instruments to be in exactly where they're in the spots where you want them to be, and that the orientations are all perfect, and that the amplitudes of each component is also perfect, so that any amplitude variation can be ascribed to something in the earth. Well, here's what you actually get. It's hard to perfectly put in and orient a nodal seismometer with a compass, and each component, I mean, the seismometers aren't perfect. They have different gains and whatnot. And when you do a spatial derivative, as shown here at the bottom, we're basically, this is an idealization of a first order derivative to get a spatial gradient. We want the displacement at one spot and subtract the displacement from another spot, delta x away from the center. And this is a second order error in actual position, but there's this A term, this unknown amplitude, which can give rise to errors, first order errors in this derivative. So this is a real bugaboo in gradiometry. I want to be able to control that as much as possible. So let's kind of step back from Oklahoma and zoom over to California for a second. Here's an array that Frank Vernon put in at Pinyon Flat. It's about the same dimension as the Oklahoma array. It's about 600 meters on a side, consisting of broadband instruments. And I was looking at this array to be able to calculate horizontal displacement spatial gradients that I could turn into horizontal strains to then compare to horizontal strains at the PBO strain meter, BO84, in pinion flat. But it has the same problem. I'd like to know exactly what the relative amplitudes for all those components, horizontal components of the stations are. Plus, I have to know what the orientations are to a very high precision. And we're going to look at this 7-level recursive gradiometer. It has 112 elements, 100 to 103 actually made it out of Oklahoma. And so we'll look at this array too and to see how it works. So I'm going to show you the inverse method, an application to the California array, and then application to Oklahoma. So here is the method. The assumptions are sort of stringent. I'm looking for a gain for each component. And so what I'm going to assume is that I have a very small array, that the entire array records the same wave field. And this is actually satisfied quite nicely with a teleseism, long period teleseisms with horizontal wavelengths that are greater than 10 times the array aperture. I'm going to assume that the instrument is misoriented horizontally, but not vertically, and that each component of the ground motion has a different amplitude multiplier. I also have to assume that the instruments are built correctly, that the horizontal components are actually orthogonal to each other within the instruments. As we'll see, that it seems like we can get very high precisions out of this inversion, and it's getting down to the point where the precision seems to be greater than what the instrument manufacturers actually advertise. And so what I want are all the relative orientations of the sensors and the amplitude multiplier in front of each component to be able to see what the relative amplitudes are between sensors. So let me go through pretty quickly the deal with a linear inversion. This is all going to be done with linearized inversion. If we just look at the vertical components of an array, what I'm going to assume is that each component, here are two of them, Z0 and Z1, record the same ground motion, and they have an amplitude multiplier in front of them, and that we can solve for use of Z in terms of one of those components of motion, and get the other component of motion in terms of our reference component of motion. That's all very straightforward, and basically we can take very long time series seismograms and take the inner product, which is just a zero lag correlation, and basically take the ratio of the zero lag correlation of one sensor to another over the autocorrelation to get the amplitude ratios. So we get, this is one number over one number, and we get that ratio. We can take that ratio and then take the logarithm to get a nice linear relationship between the amplitude multipliers, and also have a constraint that the log of all those amplitude ratios come out to be 0, which means it's an amplitude of 1. So we're going to average over the entire array and say that it must have an amplitude of 1. And put this into a standard linear inverse problem. This is from Van der Kar and Crossan, who used it for relative times. It's the same problem. And you can solve this problem and get all those amplitude multipliers with this constraint, that the average comes out to 1, or the log of all of them come out to 0. Now, the horizontal components are a little bit more complicated. Here is our true north and east. Here is the ground motion, so function of time, and we have 3 components of it from this teleseism. Here's our station that actually records this ground motion, and it's misoriented by some delta. And so we can write the east-west and north-south components in terms of these horizontal ground motions. Ignore the math. The important thing is that we have the relative amplitudes between all the other east-west components and the reference east-west and north-south components of our reference station. We solve, and we take all the seismograms, take all these zero lag correlations of the seismograms, and pose an inverse problem to find all the relative amplitudes and relative orientations. So with this procedure. It's not truly linear because we have 4 coupled nonlinear equations and 5 unknowns. We have to fix one amplitude, and so the east-west amplitude for the reference station is chosen. And then there's also the east-west to north-south amplitude ratio at the reference station is turns out to be weakly constrained in this problem. But that's not a real problem. Well, here's the result for the pinion flat array. Here's the array again, all the circles in the broadband, and basically the least squares residual for these horizontal component inversion drops by over an order of magnitude and gives you this kind of result. Here are the amplitude corrections. So these numbers are what you would multiply times in this case, the vertical component of a seismogram to get it to 1. And we see that the precision from some 40 teleseisms that were used to find the variation in this number is really quite high. It's on the order of a couple of tenths of a percent. And we can find the amplitude ratios themselves very accurately and correct this stuff down to much less than 1%, which is usually the advertised resolution or the advertised tolerance of the instruments in terms of gains and everything else. And so this is for the all the stations that array. Here are the east-west components and the north-south components. There's a little bit of change with time, but not much. And we can actually see different instrument types in this inversion. If you look at it, look at all the residuals of the log amplitude factors, we can see that the STS2 is down here. That's the PFO station. An STS5 station has a very nice peaked distribution. They seem to be made very consistently, and the nanometrics T120s also show up very nicely as a separate distribution in the residual. And so we can correct all these instruments to the same type, essentially, with this inversion. You can see the scale is the distribution here. The half is like, this is like 0.5% in one sigma for the vertical components, and it's a bit larger for the horizontal components. The azimuth deviation, the orientations of the instruments is crazy. Here's our relative, we're taking everything relative to BPH1 at this array, and that by definition is 0. But the errors in azimuth of many of the stations are really quite small. And it looks like we could resolve relative orientations much better than 1 degree. And so that 1 degree is kind of the limit that you can do with a compass in the field. And so using this technique, you can actually get a much higher resolution in terms of lining up your instruments. And this is exactly what I need to be able to calculate those amplitudes. Okay, well, on to Oklahoma. And so we don't have as many teleseisms as we do in California. And so far, I have 3 teleseismic P waves recorded by the Oklahoma Gradiometer. We're going to be looking at waveforms that have been filtered from 3 to 2 seconds period, and we're going to look at 300 seconds, 5 minutes of the 3-component data, and we had 100 to 103 stations in this inversion. I should mention for the pinion flat data, there was an hour of data for each one of those teleseisms. Quite a lot of data. Here's an example of the really good teleseism on the Oklahoma experiment. The gradiometer, you can see, shows like amplitudes of 50% changes within the gradiometer. For the vertical components, it's harder to see in the horizontal. There's some outliers, a couple instruments here and there that aren't perfect, but in general, they kind of track each other quite nicely. The Gole broadbands are also very nice. So here's the result just for the first ring the stations, I'm sorry, ring number 4 coming out from the inside of the gradiometer. And this is relative to a station in the first ring, actually the first station of the whole thing. And with 3 teleseisms, one of them which has quite a bit of noise to it, and so I have to do some more study with the effect of noise on this inversion. Basically, you can see that we occasionally get very precise amplitude corrections with very high precision. In other places, the precision is more like a few percent. And so it's not quite as good with the nodal seismometers so far, but we can see that the corrections can be quite large. So here's the east-west component. We have a 40% change from 1 for this particular station. And so this is a very important correction to apply to be able to do wave gradiometry. And here is a view of the orientation of those seismometers in the field around ring 4. And so they vary pretty much like plus or minus 5 degrees. So that's about all I have to say. I haven't actually done any gradiometry calculations at the moment, but I have some high hopes here. I think the data are excellent. The correlation of waves across the entire experiment is amazing. And I think there's this experiment has a very high potential for actually answering the questions I want to get at. So here are the conclusions. Have an inversion method to do the relative amplitudes and orientations of a dense array. Applied it to pinion flat and got very high precisions and a little bit less precise for the Oklahoma gradiometer. So thank you, and I'll take any questions that are out there. Here is the IRIS Enid field annex that we had last summer.
A lot of memory of that. Thanks, Chuck, very much. Excellent talk. Folks out there, if you have questions for Chuck, please feel free to send those in. We've got a bunch that have come in so far, so I will start firing those off here. First one wants to know, what was the time gate used for your phased array velocity estimate? It says correlation always gets worse the further from the first P wave cycle, so estimate can depend heavily on the time gate.
That's a good question. Let's see, I'll go find it. It was 6 seconds. So I took all of that data that was in that window. Here we go. What you see is what I put in there. Also, it's longer than 6 seconds. It's almost 8 seconds overall. So it includes all this stuff. Yes, you would get a better answer if you just took the first few seconds. So even with all the, that's a very long time window, it still did amazingly well.
Is there a reason you chose to do a longer time window versus just focusing right in on the P wave?
No reason whatsoever.
Okay, all right, fair enough. Let's see, next question. So a couple of questions about wondering about these changes in amplitude. What causes the variation with time in those amplitude correction factors? Is it instrument related, or is it site response, something related to the installation?
Okay, so with I think you're speaking to these kinds of plots.
Yes.
Yeah, there's some changes with time. It's due to when I was looking at the data, the longer period data are really quite nice, and even without any correction, they sort of track each other very nicely. But there are very local sources of noise, and so noise does come into this in terms of basically there is some scattering under the array that there'll be slower velocity waves that they could be different for the different teleseisms that come through, and kind of contaminate the answer a bit. But the overall message is that we're looking at changes or sort of the precision in this measurement, which is better than the manufacturer's sort of precision that they advertise. Now, how I interpret that is that the instruments aren't changing very much with time. I read a paper for the group in the USGS who were looking at instrument corrections, and basically they found that sometimes there was some temperature dependence. Now, these are buried instruments, but there could be some other independent variables that are changing the response as a function of time.
Okay, a few questions about these the amplitude corrections. One here: are the amplitude correction factors really frequency dependent? And then, kind of related to that, what is the minimum station spacing within the gradiometer, and what is the highest frequency that spacing works for?
Let's see, 2 questions. Okay, so in general, yes, these amplitude corrections will be frequency dependent. You can imagine that everything can louse up this this calculation. The phases, the seismometer, everything. All the theoretical instrument responses were taken out of all of these data before this correction was found, by the way. I failed to mention that again. So they are frequency dependent. I did try breaking it up into 2 bands, a shorter period and a longer period band. I got the same answer for the pinion flat data. And let's see now, the minimum, the gradiometer, okay, so the gradiometer is 800 meters across, and we're looking at 2 to 3 second P wave, teleseismic P waves, which are going at maybe 15 kilometers per second, and so that's a 30 kilometer wavelength, and so. But your question had something to do with what's the highest frequency could be.
Yeah. Well, so they said, what is the highest frequency that spacing works for? And it says, why 0.3 to 0.5 hertz? What about 3 to 5 hertz?
So you're asking about the frequency content used in the amplitude correction?
I think that's what they're asking about. Yes.
Well, you can see move out when you start going to high frequency, and so the assumption that the wave field is simultaneously the same at all sensors breaks down. Then you'd have to apply a move out correction. I'm also worried about what is the what would be the frequency, or are there errors in the frequency response? Using the nodal seismometer response at 3 to 2 seconds is right at the edge. I realize that, and so there does have to be some more work on looking at the response at higher frequency.
Okay. So sorry, this follow up on this. This is let's see here. Are there particular criteria that you use when choosing a reference station, and how important is the choice of a reference station to your results?
I've worried about that quite a bit. The reference station obviously should be one that works. It doesn't have any obvious problem with it, with transients and noise sources and things like that. That's where the reference station is important only for the horizontal component sort of application. So the answer is that ideally you'd probably want to use every station as a reference station, but then I tried to sort out, well, what will the relative amplitudes and relative orientations actually mean at that point, since they really depend on the initial. You have to fix one component. I chose the east-west component of the reference station for the horizontal components. What will that mean in terms of the overall correction for the array? And I've used a couple of different stations, and you get very nice, precise answers, but obviously the answers will be different because of the reference station you use. Now, in gradiometry, you can't ever find the absolute, doing this way, you can't ever find the absolute east-west or north-south direction. You can find something that's like an array average. And so you could take a reference station and do this for all the stations as being a reference station and finding all the relative orientations, then choose a reference station that gives you the median, or the best estimate of what you might think is north-south or east-west. And I think that might be a viable way to actually choose the station.
Okay. Another question here. Have you thought about using robust methods to identify the outliers in the amplification of each of the sensors in the array?
No, I haven't. What sort of robust measures?
They didn't specify. They just asked about trying to determine outliers. Well, there's a second question here from the same person. Are you looking at the individual calibration sheets from the manufacturer to find out if they reported a different amplitude for a particular sensor?
I was relying on IRIS for that, and
it's just going off a spec, I think, but yeah.
Yeah, I think so too. Just the response file that comes with the data. Okay.
Sorry, I goofed up on an earlier question when asking about this minimum station spacing in the gradiometer, and what is the highest frequency that spacing works for. Just kind of this was specifically in reference to gradiometry. So wondering if there's a maximum frequency that you can do that, set up that gradiometer for.
Yeah. Okay. So you have to talk about what phase velocity you want to look at. And so if you have a P wave going across it at 6 kilometers per second, basically the wavelength for a 1 hertz wave, P wave, would be 6 kilometers. And so this gradiometer overall would be really good for that. If we go down to the inner ring, I think that was, what was it? That was something like 27, less than 100 meters, about 100 meters across, right? So we're talking about so factor 10. This would be a 10 hertz P wave, I think, for the innermost ring.
Okay. Great. Well, yeah, sorry, Kent just jumped in here to remind me that we've got just over 3 meter spacing on the inner ring between those stations. So pretty tightly packed.
So 1, 2, 3, 4. Yeah, that's 12 meters. Yes, man, I'm off by a factor of 10.
It happens. Okay. Well, I think it's time we wrap up. But I just want to again thank both of our speakers today, Nori and Chuck, for giving us some fabulous insight into this this exciting data set that we've got available. The data set is public and freely available. You can get more information about it at www.iris.edu/wavefields. And thanks again, everybody, for being here.